Good afternoon, everyone. My name is Gia Zhang from the University of Missouri. It's my first time to go to the Nebraska. It's really beautiful city in Oklahoma, and it's my really pleasure to present my first published work in my fourth year PhD program. And yes, the title is Mechanistic Insight into the Electrolyte PFAS Interfacial sorry interaction. Yes, in our group, together with Jiaming, with Jeffrey, we do a lot of work with PFAS, the immigration and transportation of PFAS in the groundwater or in the soil. But truly, we maybe not fully understand what is the mechanism of that transportation in the interfacial area. So we do this work is we just answer a very small question, maybe, and we want to make it deep from the molecular simulation and the quantum chemistry analyze this direction. And, oh, sorry. Yeah, I want to make it directly to my research. So the research direction in our work is how the salt influence the interfacial activity of PFAS in the air-water interface. And we want to make a deeply understand that what is the molecular mechanism of this process. Maybe it is electrostatistics or hydration or orbital polarization, something like that. We are not sure. So we do this work. And the motivation of our project is that we know the PFAS is surface active in the water or in the water air surface. So, and the salt also changed the surface activity a lot. And there are current models in the recent work. Current models are more pay attention to the bulk ionic activities, not the very specific ions. So, and there are some mechanism or the molecular levels under understanding is needed to be improved. So that is why we do this work. And the background is, yes, PFAS, we pay a lot of attention to do what is transport, but the mechanism is not clearly. And we select the sort based on the master series. It's kind of a sort satisfaction based on there are different interaction with protein in water. So we think the protein and the salt looks really similar to the PFAS and salt. So we introduced this interaction method into our project. And the third is the recent computation and examination works have shown some potential that we can do the PFAS in the water air surface with DFT calculation. And then we found the gap. That is what we can do is we can base on the microscope measurement, some experiment. We collect the data and do the molecular simulation to know the deep. Okay, here is the method what we use. The first for the experiment is pendant drop method to measure the surface tension. And then we do some data analyze for the experimental data. And for the modeling and simulation, we use DFT. And here is the PFAS we select in the work. They are mainly based on the chain length. There are some contains about 5 carbon and some contains 8. And the lower is salt we select in this work based on the master series. And then we put our experimental data in this equation to and use the data analyze method to match to identify whether the data is match the equation, and we can group the data into maybe 3 or 4 clustering, then they are useful to us to build a model in this process. Okay, here are the results. We can say from the surface tension and the salt concentration, this figure, we can say as for the calcium, even as very low concentration, yes, the surface tension decrease very fast. But for the zinc, maybe I make something wrong as the picture D, they are zinc. They only at the very high concentration, they have some reaction to the surface tension. And then for the surface tension and the main ionic activity, we can say as for the short-chain PFAS like PFBA, so all data fall into one line, and for the long-chain PFAS like PFOS, they are separate. Yeah, so that's a different. And there is surface departing contents with the ion strength. We can say that calcium can change this contact has even very low concentration. And here's the result for the experiment part. We can say the long chain of the PFAS really influence our experiment result. And we have said that the recent activity modes cannot cannot describe the whole process. They are insufficient. So we put our experiment data into this pattern recognition to analyze it. We found they are organized into 3 groups. So group 1 is the long-chain PFAS with divalent cations, like the PFOA and the calcium. And the group 2 is for the short-chain PFAS with the DI water. And the third group is some special cations like the sorry. And here is the pattern recognition too for the gamma 0, which means the baseline surface tension. We can say based on the long chain changed, the gamma 0 decreased. And for the gamma M, which means the minimum, we can say they are also very different. Yeah, that is result of our data analyzing process. We can say that it's easily to say our data were grouped into 3 groups, and they are really based on the long chain and the type of the ions. This is a really important result that we can observe. And then we do some DFT calculation to make sure what happens deeply and what is the mechanism based on that. We can say, as for the calcium, the strong electrostatic binding as a PFAS head group. Maybe that is establishing absorption without major optical dissertation. That makes our experiment shows like it can have the surface tension decrease at even very low calcium dosage. But as for the zinc, as it has a high binding energy with significant homolomal delocalization, indicates a strong polarization, but it is limited by the hydration. So that is the result why only at a really high concentration, zinc has the effect to the surface tension. Okay, here is our summarize of our proposed mechanism of this whole process. We can say as for the calcium, the strong electrostatic binding make it reacts very strongly. And for the zinc, the potential electronic polarization with the hydrogen process. Sorry. The hydrogen process makes the surface tension only decrease at really high concentration of the zinc. And as for the cesium and the calcium, the co-localization and the hydrogen bonding make their surface tension changed on Euro. So we have this three mechanism framework for our conclusion. Okay, here are some takeaway questions for our presentation today. First, that's the PFAS, how the PFAS influenced by the sort, mainly based on the long chain of the PFAS. And the second important factor is that the type of the different ions is also really important. And our experimental and simulation data are much very well. So that is smart but well organized work. Thank you. Thank you for your attention today.
One question?
Okay, Pam.
So you did this study based on the modeling and DFT, and you found that like the specific ions like calcium and zinc, they may have a strong effect on your PFAS absorption at the air water interface. Have you ever considered to use experiments like a full fractionation for PFAS removal with constant PFAS? Either you collect it from the literature or do the test by yourself to double check whether your model is actually reliable or not. That's my question.
Yeah, it's really good question. Yeah, we have considered about it, but we have already not done that. Maybe we will put it in our future work. Thank you.